We have Tove Larsson today, who is Assistant Professor of Applied Linguistics at Northern Arizona University in the US, and she's also affiliated with Uppsala University in Sweden and the University of Louvain in Belgium. And Gregory Hancock, who's Professor and Distinguished Scholar and Teacher and the Director of the Measurement, Statistics and Evaluation Graduate Program at the University of Maryland. And we're very grateful for them to be here with us today. And well, I'll just let them do the talking, and if you want to say hi to our participants, and then feel free to start with the workshop whenever you're ready.
Excellent. Thank you so much, Rafael, and everyone for organizing this, and thank you everyone for coming. We're really excited to be here. So we'll be talking about structural equation modeling for corpus linguistic data, right? And just a short little caveat here that this is a 2-hour session, meaning that this is very much an introduction to SEM, and we can't cover everything there is to know for obvious reasons. There are, books and long courses, and several of them, and so on. So we're hoping that we, in this 2-hour session, are able to, and this is a metaphor that Greg uses that I really like, open some doors for you so that you can see, so we can kind of shine a light in there and say, okay, in this room we have this, in this room we have that. And if you find that some of these techniques are potentially relevant to you and to your research, then please, after this workshop, go out and learn more about them, because again, we can't cover everything here.
And it's not as scary as the red room would seem to suggest. I don't know where you got that picture. It seems a little, it's not really that scary.
Right. It's, red is a nice color. Happy color. Okay, so we'll be, this is the structure of this workshop today. So we'll have a lecture portion, a hands-on exercise portion, and a conclusion looking ahead, just final few words on that. And since we'll be recording the first part and nothing after that, we decided to divide this up very clearly so that we have the lecture portion first and then the hands-on exercises. Whereas had we not been recording and so on, maybe we would have mixed them a little bit more, but just so you know. We're planning for about 50-50 in terms of percentage spent on the lecture versus the hands-on exercises. And for the lecture, I'll be starting and I'll be giving you a more of a conceptual overview based on the article that I believe that you've read in preparation for this workshop, talking about structural equation modeling, what is it, measured variable path analysis in particular. And then I'll continue to talk a bit about benefits for corpus linguists specifically. And then I'll hand over to Greg to talk about this in more detail, how does this work, and so on. And then let's try it out. Let's do this together, and we have some exercises. And yes, a little bit of R, but mostly non-R stuff, just more kind of conceptual things so that we can then set you up to be able to do this in R. We'll be basing this on the article and the data that we have sent out to you through the organizers. Thank you very much again. And then the concluding remarks. Okay, so for me, this all started back in 2019 when Greg and I got talking, and he asked, do you have any training in structural equation modeling? And to which then I had to respond, well, since I don't know what it is, I suppose the answer is no, sorry. And then he said something that's really stayed with me, and that is that he said, warning, it might just change how you think. So this is very intriguing, right? And we're going to be unpacking this during this workshop here, because he was right. At the time I was like, yeah, maybe, but it actually did change my mind and change how I thought about things and all that. And this all resulted in the article that, again, you have probably read for this workshop. It's available open access. And You might want to, depending on your previous experience with SEM and with statistics in general and so on, you might want to return to this article after this workshop. And our hope is that you'll then be able to understand all the different steps better, and that you can then use this article perhaps more as a kind of step-by-step guide for you to be able to apply these methods to your data, to your research questions, and so on. And also on that topic, I could perhaps mention that we're not assuming any previous knowledge or any previous experience with SEM at all. We are assuming some familiarity with regression and kind of basic statistics methods and so on. But yeah, we're assuming no SEM knowledge at all. Okay, and on that note, what is it? So structural equation modeling, SEM, is a family of statistical techniques that's widely used outside of corpus linguistics in second language acquisition, education, field of education, psychology, and so on. So a lot of fields use it quite a bit. We don't, for like we talked about in the interview, I would say no good reason. There are some exceptions, some people who've used it, and also some people have started using it. I saw, for example, in there's a Learner Corpus Research conference coming up in September, and there were some talks there that used SEM, which is really exciting. So this family then covers techniques such as measured variable path analysis, confirmatory factor analysis, latent variable path analysis, latent growth curve models, mixture models, just to name or mention a few, excuse me. There are a lot more in this family too. And again, remember this kind of shining a light through a door, weird red color, and all that. This is just, some of the stuff you could be looking into for your research. And so people who have heard of SEM are likely to maybe associate it with something like latent growth curve models and have it be something really overwhelming, a little bit scary maybe, and really confusing and not very manageable. In short, they actually aren't scary, or they are very manageable and so on, but they're advanced, right? So we decided for the article and for this workshop to start kind of more in the more basic half or whatever section of things, and talk about measured variable path analysis that will can look something like this, right? And so this is a path diagram of a path model, and we'll be talking a lot about such models and this way of representing things today. So just to make sure that we're on the same page, what are we looking at here? So this is a model where we hypothesize that there are two independent variables. We could have lots or several, where there's just one dependent variable. There could be more. We just have one right here. Another term that we use for independent variables is exogenous variables, and then dependent variables endogenous. We won't be using this here, but just to, in case you've read other articles and so on, just to map that onto this. And then we will have an error term, residual, and Greg is going to get back to this a bit later, and covariance, where we have this double-headed arrow to mark the covariance. And just again to make sure that we're on the same page. So variance, as you may know, measures how far a set of numbers is spread out from their average value. And covariance then is a measure of the joint variability of two, let me start sharing again, of two variables. Okay, please hold. And so when we talk about covariance, we're in the unstandardized universe. And let me get to the right slide. And then when we, but you might be more familiar with when we're talking about the standardized universe, and that would be then correlation. So we have, in this case here, we have variables x1 and x2, and we allow them to covary. And so in this case here, there's, fairly, we can just see from the graph here, fairly strong covariance or correlation between the two. Okay, and then we have these single-headed arrows that are direct paths, or their paths, direct effects. So that in this model here, we're hypothesizing that x1 has a direct effect on y, and x2 has a direct effect on y. And then we also have the little direct effect from the error. Okay, so again, just to kind of bridge the gap between the different frameworks. So we have multiple regression, and what would that look like in this framework? So just to show you that. So if we have a multiple regression model with 3, and this is also we're gonna be returning to this in exercise 1. We have 3 independent variables. So noun phrases per clause, cohesive devices, personal pronouns, just to give an example here, and 1 dependent variable, so holistic TOEFL scores. And so direct effects, and in regression, we have to have all of them linked up like this. They have to all covary, because that's the default, and that's the yeah, we can't get around that. Whereas in our SEM framework, we actually have a lot more control there. So, and we'll return to that in a moment, and then we have our error term as well. Okay, so the role of theory is very central here, theory and/or previous research. And so just to give you a little bit of a family tree of what's going on here. So beginning of time, there was regression, exploratory factor analysis. And on the regression side, we then, or some smart people, added theory, and then we got path analysis. So path analysis is regression plus with the addition of theory or previous research. And then on the exploratory factor analysis side, add theory, and we get confirmatory factor analysis. And these two, path analysis and confirmatory factor analysis, along with others, as we saw earlier, then make up the SEM family. And this role then, or the importance of theory. So in this framework, all models are hypothesized based on theory or previous research meaning that we're not using these for more exploratory questions and so on. There are some members of this family that have more of an exploratory flavor, but kind of primarily hypothesis testing. And this means that all the paths, all those arrows that we have in there, whether bidirectional or unidirectional, are added and removed a priori before we even run anything, based on our beliefs, based on theory, based on previous research. And this is really important. So we're going to be using register, this example with register and discipline quite a bit. So let me just introduce it here. So if we have this idea or this theory about how register and discipline affect something, so in this case, complexity features. So then we can specify that in our model, and that's then what we test. So register and discipline here are our 2 independent variables. So now we've kind of turned the view here. And then we have 3 dependent variables. So adjectival modification, prepositional modification, and nominal modification. And we'll return to this more in the worked example at the end there. So anyway, so our theory can then help us decide which arrows to add or remove, right? And so if we were to just put everything in there, because our theory tells us that everything is linked up, although there's a bit of an issue with that Greg is going to return to later about linking everything up. But so let's say that, okay, our theory says everything's linked up, then we would have everything, so register affecting all 3 of the dependent variables, discipline affecting all 3 of the dependent variables, and they're all connected, so they all are allowed to covary, right? So this is kind of the maximum. I haven't added the error terms here, but this is kind of the maximum number of different things that could be hooked up. But then more likely our theory will say something like, well, no, actually register only affects adjectival modification and prepositional modification, and discipline only affects nominal modification, say. And then that would be our model 1 to test. And this is another thing that we tend to do. I say we, because I'm, since 2019, I'm part of this family of cool SEM people. So we tend to have more than one model. So we test 2 competing models, maybe 3 competing models, and they're all specified based on previous research then. So model 1 would be this, and then model 2 would be, okay, well, actually, I have a competing hypothesis here that says that register affects such type of modification, preposition modification, but discipline actually not only affects nominal modification, but also prepositional modification, so the red arrow in here. And that would be the competing model, so model 2, and then we test to see, okay, which one, if, either one has better fit. And again, Greg is going to return to this in his part of the lecture, what good fit means and all that. So SEM is a process, unlike more perhaps less advanced tests where you have things like a t-test or something, you just kind of run it and you're good, you interpret it and so on. But this is a process where that allows, for the assessment of typically causal theories involving measured and potentially latent variables. We won't be talking about latent variables here much, but they exist, or they don't, or whatever, that are hypothesized a priori to explain the characteristics of measured variables. And so the process looks like this, and we'll be going through these steps a bit more in the hands-on session, where we have model specification, model identification, model estimation, data model fit evaluation, possible model modification, and then finally result interpretation. So again, we're moving through these steps. And you might have noticed something here. So we say allows for the assessment of typically causal theories, right? And this is something that tends to make people a little bit uncomfortable, because if you've taken, I guess, any statistics course, you're likely to have come across this, right? Correlation does not imply causation. So we must not talk about causation, whatever we do, right? Actually, a teacher that I had in one of my stats courses had us repeat this, like say this out loud together in the class, correlation does not imply causation. And that means that we tend to be, or have to be, very careful when we talk about how X is associated with Y, or X predicts Y, and so on, when we're in talking about regression and so on. What SEM does, though, is that it kind of flips this around to say that causation, so correlation may not imply causation, but causation implies correlation. And so we can have causal relations, or rather, okay, let me start over here. So we can't identify causal links using SEM in any way. We hypothesize what those links might be based on previous research, based on theory, and then we test that to see, if this actually corresponds with what we see in the data. So there are also some criteria that need to be met for causality, and you can read more about that here. So SEM is a framework for testing and assessing the magnitude of those relations. Again, we're not identifying it, we're not kind of finding it, we're testing our beliefs about these causal links to see if it actually makes sense when we have our data. And that allows us to say things like X has an effect on Y, or X causes a change in Y, right? So we're actually using more kind of causality language in a way that we might have wanted to do in the regression world, but we weren't able to, really. So just to kind of sum up this part a bit, so SEM is a process. It's a process that contributes to answering what are the mechanisms responsible for why variables vary and covary the way they do. by testing a priori theory-driven structural or causal, so same thing, theories. And path diagrams are the ones that we looked at earlier with the little rectangles and arrows and all that, are graphical representations of the relations hypothesized to underlie a system of measured variables. Okay, so this is, if you've never really thought about this, then there's a lot going on here, right? A lot that takes a while to get used to. So why why spend time on this? I mean, you're already here, which we're very happy to about, but this requires a bit of time, right? So why bother really with this new set of techniques? So what are some benefits for corpus linguistics, corpus linguists specifically? So I'm going to talk about 3 here. There are more, but the main ones are flexibility, and I'll talk about each of them a bit more. But flexibility, so where we let the research question govern what technique we use. And then secondly, allows us to move toward model-based reasoning. So we're then less reliant on the more narrow NHST paradigm. And again, we'll turn to what this means in just a second here. And allows us to move toward cumulative research or cumulative knowledge building in a more hypothesis testing framework. Okay, so starting with the first one here. So flexibility. In regression, so multiple regression, for example, we have this one way of linking variables up so that we have one or more independent variables, so that's flexible at least, but then we can only have one dependent variable, and all the independent variables are going to be linked up in this way. So that's not particularly flexible, right? And that's, I think we're so used to seeing the structure that we don't even think about it. We just kind of design our studies so that we'll only have one dependent variable, and then we have some independent variables, and then we run it, and then we're good. But what if we have questions, research questions that have multiple dependent variables, something like this, right? So 2 independent and multiple and 3 dependent variables, or what if we have reason to believe that one variable mediates the effects of another variable? We won't be talking all that much about mediation and moderation here, but so we have something like, for example, working memory affecting reading comprehension, which in turn affects the scores you get on 2 L2 proficiency tests or something like that, so that there's something that affects something else that in turn affects a third thing, and so on. Or what if we have unmeasured variables, so-called latent variables, that have a causal effect on a set of measured variables, or something like this? Again, we figured 2 hours, we won't have time to go into that, but there's a lot more to learn about latent variables and that world. And also, what if we know that the independent variables don't actually covary, right? So that we shouldn't be connecting them like that, where we have something like, I don't know, weight and frequency of adverbials or something like that, that it just doesn't make any sense for us to say that they're likely to covary, and yet we do in regression in a way that we don't have to do here, unless we believe that there is such a relation between them. And finally, what if we feel confidence based on previous research that we already have a stable effect size prediction for a variable, and we want to test that hypothesis, so that we want to test something like this, then we can with the SEM framework, because it's very flexible from this perspective. And second, then it allows us to move toward model-based reasoning. And this is where this becomes especially relevant, where Greg, says, okay, you might just change how you think, and I would say it did. So model-based reasoning, we're moving away from the more narrow null hypothesis significance testing paradigm, so the NHST paradigm, toward model-based reasoning. And so what is this? So it's a mindset where relations among variables are viewed as part of a larger explanatory system, and one which is evaluated as such. So it's more kind of big picture thinking already there. And I'm going to unpack this in the next couple of slides here. So in the NHST, the null hypothesis significance testing framework, we find things like regression, chi-square, t-tests, and so on. And here, differences or relations found in a sample are compared with this null hypothesis, right? Stating that in the population, there's some, typically 0, difference or relation. So that's what we do, and I think we're all familiar with that. And then we say that if there's sufficient evidence to reject this null hypothesis, then the difference or relation is deemed statistically significant, and a difference or relation other than that specified in the null hypothesis, so higher or lower, is assumed to exist in the population from which the sample was drawn. So just to kind of talk a little bit more about that, so we have this null hypothesis saying, okay, there's no difference, and we have, or potentially we could have other null hypotheses too, but and then we have this alternative hypothesis saying, yes, difference, there's a difference, right? And then we look at our p-values and we see that, okay, it's below 0.05, if that's our cutoff point, our alpha level, then, okay, less than 0.05, we're good, we're in this alternative hypothesis, we can reject the null hypothesis. And if it's above 0.05, then, okay, sorry, we can't reject the null hypothesis. The problem is just that something like 0.049 would lead us to reject the null hypothesis and instead go for the alternative hypothesis, whereas a very, very similar p-value would allow or would lead us to choose a different path, so reject the null. So this is a very rigid dichotomy, one that's somewhat or very, I guess, arbitrary, which a lot of people have pointed out. Something that's particularly relevant to us in corpus linguistics is that we tend to have large samples, and p-values are sensitive to sample size, meaning that we're likely to have a lot of things be significant or just come out as significant, so that we can reject the null more or less for anything almost, because we have so much power. And also this is very imprecise, and this is where we'll be focusing our attention to here, where we reject the null to accept so that we can talk about the alternative hypothesis instead and say, yes, there's a difference, but that's not precise at all. Like there's something going on there, we don't really know what, but we know that we can reject the null. So I'm going to read a quote here from Rogers about model-based reasoning. He says that to fully appreciate the importance of this shift toward model-based reasoning, we must recognize that the epistemological focal point has completely shifted. He says that within the epistemological tradition emerging from NHST, the focus is the null hypothesis, which we assume until it can be rejected in favor of a reasonable but broad and relatively unspecified alternative. The post-revolution focal point is no longer the null hypothesis, it's the current model. And this is exactly where the researcher, the scientist, should be focusing his or her concern. For the researcher, scientist researcher, his or her own research hypothesis is the natural focus. So again, changing the way we think about things, right? So just one slide about what this really means here, kind of comparing the two. So in the NHST framework, we ask, should we reject or retain the null hypothesis? Whereas in this kind of model-based reasoning, from this perspective, we ask instead, should we reject or retain this particular model or parts of it? So that we have this very specific question, really, and we're not being as vague as we are with in the NHST perspective. So to use the model that we looked at earlier, so we're looking at then model 1 versus model 2. So which model more accurately represents the relation that we have in our data, model 1 or model 2, right, or neither. And then finally, it allows us to move toward cumulative research, where, so as I said earlier, SEM techniques are hypothesis testing, right? And this gives us then an incentive to build on previous research. We talked a bit about this in the interview too, where we are as a field, or perhaps should be, interested in a topic where we actually work together to learn more about a topic and so on. And this goes back to a plenary that Doug Biber gave in 2020, where he asked the question, do we even have a state of the art in corpus linguistics? So what's going on here? And so just to very briefly describe or discuss this. So what tends to have been the case in the past in corpus linguistics is that we have a team of researchers or a single researcher being interested in a topic. They start a pyramid and they say, okay, let's learn about this topic, complexity or whatever. And then you have a second team that's also interested in the same topic, but they use slightly different methods, maybe slightly different definitions of concepts, slightly different things that mean that they can't actually be compared fully, so that they start a new pyramid. And then maybe the next group of researchers come along and they start a new pyramid. Instead, what we could do is build on each other's work more properly. And this requires some change in the way we do things, assuming we want to do this. Is not a given, but I think that a lot of topics would lend themselves really well for this kind of approach. It would require us to open science and all that, to share our materials, share our coding schemes, and so on a bit more, so that we can actually use each other's and build on each other's work. And also this changing of the mindset where we move from having this individual, let's work on this one study and then turn to the next one and so on. Instead, we're working together to build something together. And this framework, the SEM framework, can really be helpful here in that it requires us to have previous research. It requires us to have theory so that we can test our hypotheses and take it from there. And like we said in the interview, there are a lot of fields that really can't really work particularly well without this mindset where, for example, medicine, where you need to build on each other's work in order to be able to reach better understanding of that topic. And with that, I'm gonna turn over to Greg. So let me stop sharing.
Thank you. All right, before I go ahead and start up my slides, I just wanted to pull back for a moment, and then I'll fumble in front of you to figure out how to display my slides. And for some of you who have heard me use this explanation before, I apologize, but there's an analogy that I use a lot that has to do with the Legos that I played with as a kid. And I don't know if you played with Legos as a kid, but a lot of the sets of Legos that I got to play with, they would come in a box and there would be a set of instructions and you would put it together exactly as the instructions said, and then it went on a shelf or something, right? And a lot of the statistical methods that you have work one way. They come with a set of instructions. It's the t-test, it's regression, or maybe it's one of many other statistical techniques that you're familiar with. And one of the problems that Tove alluded to is that you start to look at problems in a way that are shaped, right? That's shaped by the tools that you have. When you only have a hammer, everything looks like a nail. And what we're trying to do here is to take all the Legos that you have in all of these different kits and dump them onto the floor and let you build what you want in a way that matches your research question. And that will naturally lead to things that look a little bit more complicated, that are much bigger systems. But on the bright side, you are able to model much bigger systems, because so often, as Tove said, we do these little pockets of studies that try to paint a picture of what's going on over there and what's going on over there. The problem is that they might not actually be able to be isolated. What's going on over there might be related to what's going on over here. So the ability to build some bigger system with more moving parts might actually be essential to understanding how that bigger system works. And in doing that, it means that we might have to leave some of the things that we're comfortable with behind, or at least look at them differently. And one of the things that came up was null hypothesis significance testing and our p-value. And I assure you that structural equation modeling has a lot of hypothesis testing, and it has a lot of p-values, but it also tends to view models in a much more, as I like to call, evidentiary framework where we propose the way a system works, we gather data, as we'll dive into in just a little bit. We gather data, and then we assess, we try and gather evidence to see whether or not the model that we think governs what's going on in the world is consistent with the data that we are actually observing, what we observe based on theory and what we expect based on theory and what we observe in our data. So with that, I'm going to go ahead and fumble around and try to open some slides here. Let's see if I can do it. And 12, our slides, our slide numbers might be off by 1 or something. I don't know if you were doing some magic on your slides, but I'll start into this one here. And boop, boop, boop. Let's get that going. There we go. So I'm going to go into a little bit more detail, and there's a lot more detail, right? If you don't just shine a light through that door, but you kick down that door like you're going in to rescue somebody, there's a lot of stuff in there. And structural equation modeling is not just a room, it's a room that has more doors and more doors and more doors. And what we'll do is we'll take you in a little bit more into that room, and that's what I'm going to do right now. But please know that there's so much more to it, and it's all really cool and exciting. So let's get into just a few of the key concepts here, some of which will overlap with things that Tove already introduced you to, but to help reinforce some of those, and then I'll move us forward a little bit. Some of those key concepts are going to be, and she mentioned some of these already, and I'll contextualize them a little more. The measured variables that we have, errors or residuals, what exactly are those things? The ideas of directional paths versus non-directional paths. What are all of those things? And again, you've seen a little bit about those. I'll try and say a little bit more. And then we'll get into, very briefly, some issues of model fit and variance and covariance and fit indices and modification indices and a lot more. So let's just start with some of this, or really, because you've been exposed to it just a little bit, let me say some of these things again, maybe a little bit more formally. Here we go. All right, so as you start to get a sense from what you've already seen, notation is a very big part of structural equation modeling. And part of that has to do with the fact that we start to try to understand larger systems. If someone just said, I'm doing a t-test, and that's about all I need to know, that their two groups are being compared in terms of their means. Or if someone says, I'm doing a regression with 3 predictors, you go, okay, I kind of know what that is. But if someone is doing something much larger, we have to figure out how we're going to communicate about that. And visual representations, path models, path representations really are the language of structural equation modeling in many ways. Of course, there's mathematics, but I absolutely think in terms of these notational conventions. So when, for example, Tove was representing something in a box, whether it's a square or a rectangle, that means that's an observed variable. That is something for which you have data. If you go to your spreadsheet, there are numbers in a column labeled with whatever that thing might be. Now, it doesn't mean there's missing data. There might be some missing data, which is its own exciting, maybe exciting is a little bit charitable. That's its own world. But this is something for which you intended to gather data and presumably have some. When we are trying to explain a variable, and you're very familiar with this in regression, when we're trying to explain a y or predict a y, we pretty much never can explain at all. Because there are other things that are influencing that y or explaining that y or predicting that y. So there's leftover stuff. In structural equation modeling, there is leftover stuff that we can't account for with some of the mechanisms that we're proposing. And so there will be errors attached to dependent variables, or we sometimes call them residuals. And in theory, those are all the other independent influences that are independent of the other things we have coming into our dependent variables. And we'll see these a little bit more in action, although frankly, at some point you kind of take them for granted because you know that anything that's dependent has other things upon which it's dependent. But these are two of the things that I want in that Lego box. I want residuals, I want observed variables, and have to find a way to connect things. And the connectors that Tove already started alluding to, one that's very important is a directional connector. It's a single-headed arrow, but this is where you are saying, my theory says that the thing on this side of the arrow has a causal bearing on the thing on the other side of the arrow. Who says? you say. It is your theory. And that's different from regression. I mean, in regression, your heart might think causal kinds of things, but as Tove said, we're sort of beaten into not saying them aloud. Maybe we just think them privately. And regression, frankly, doesn't make causal assumptions. Regression really is about association. In structural equation modeling, your theory about what influences what comes first, and you hard code that theory in the form of these arrows, these directional representations about the way you think variables' influences flow, almost from left to right and top to bottom, at least as we typically represent them. And so when I use the word effect, it's my theory that allows me to say that. When I use the word cause, it is my theory that allows me to say that. And the word structural really kind of only evolved as a way to dance around the word cause. Lately, we're a lot less fearful of using the C word there, but structural really was just a historical euphemism for cause, so no one would look at us. We just go, it's a structural effect, and everyone would go, but we really just meant causal. And then we will have two-headed arrows in our model, which are sometimes called non-directional relations. And you might think, oh, two-headed arrow, two things are influencing each other. No, that's not what that means. In fact, if that was something that you thought was happening, we would have two separate arrows, each going in opposite directions. A two-headed arrow refers to the idea that we think these things are related to each other, but not for the reason of any other variable that we have as part of our model. So two things are related because of external forces that are operating. And I don't mean external forces like, ooh, spooky external forces. I mean intelligence or exposure to things out in the world or familiarity with language or how much time you've been in a country. All of these kinds of things that might not have been a variable that made it in our model, but things that make you go, yeah, those would probably be related for reasons we don't have as part of our model. So these are some of the pieces that start getting put together in ways that are consistent with the way I think the world works. And some of the pictures that you've already seen, just to put some more words to this, in this model, I'm going to draw on the screen, which probably means I'm going to obliterate it. But these variables right here are independent variables according to this model. And those variables are allowed to covary. I say allowed because you're in control. Structural equation modeling is all about control. It is the technique for control freaks like myself. That's a big admission for me. So when we put a two-headed arrow, that is you saying, no, I have a theoretical reason to believe that those are related to each other. Regression, all regression does is regression, as Tove said, allows them to covary. And maybe beyond that, you kind of pray they don't covary too much to cause multicollinearity problems. In this world, if we put a two-headed arrow there, we say it's because we think there's a reason for them to be related. If I didn't think there were a reason for them to be related, I wouldn't have put the two-headed arrow there. Again, I'm trying to communicate the idea that you have control over the aspects of your model. In this particular model, this hypothesizes that there are three variables that are dependent upon some of these things. For example, this dependent variable is hypothesized to be dependent upon those two things. Who says they're dependent upon those two? My theory says they are. This variable, same. This variable, no. This variable is hypothesized only to be influenced by that second independent variable. Now, what's not shown in this figure is the fact that these dependent variables have other things influencing that would be in the form of errors. So if I were to be complete, which sometimes we will be and sometimes we won't be, there are these other things, these residual influences on those dependent things that sometimes we just get too lazy to write, but we know that they're there. That's an example. Already it starts to leave the world of multiple regression in the sense that, wait, which is my y variable? The answer is you got 3 y variables, and standard multiple regression is not even equipped to handle multiple dependent variables. What about some other pictures? This one, this nice model that Tove showed you earlier, is a mediation model. This variable is independent. It is hypothesized to influence that variable, which in turn is hypothesized to influence those. Is this variable in the middle an independent variable or a dependent variable? Well, it depends who you ask, right? It's dependent as far as the variable that comes before it goes, but it's acting like an independent variable there. The beauty of this framework is that we can mix and match and build something out. If someone came to the party with just their regression hammer and they said, well, this is my theory, what am I going to do? They would probably start breaking it up. Well, I could do something regression-y here, and I could do something regression-y here. The beauty of the system is that we can put it all in one place and assess it comprehensively. Here's a different type of model where we have two independent variables, and you'll notice about these two independent variables, there's no two-headed arrow. Why? Because the researcher didn't think there was any reason for those to be related. That is part of the theory. What you see here is part of the theory, and what you don't see is part of the theory. What I mean by that is this variable here is hypothesized to influence that variable here completely by being mediated by that variable in the center. That is to say, there's no additional direct effect there. Who says? Theory says. And that's what you're doing. You're putting in the paths that you think represent processes that are operating, and you are leaving out or zeroing out those that you think have no theoretical basis. You're essentially putting restrictions on the system, and we'll say more about that. And things get even more fun. Oh my gosh, and here's a picture that we are going to beat to death with you throughout our time together today. Here is one that says we have two independent variables, and there are names associated with them, as you will come to be more and more familiar with. Three dependent variables, and here's where things get really weird. Those three dependent variables, this isn't the weird part, all have residual influences on them. And here's what we're saying, for reasons we'll unpack a little bit later, that those residual influences, those residual influences themselves have a reason to be related to each other. Oh my gosh, I couldn't possibly explain that. Tove will have to explain that a little bit later. But again, flexibility, that's what we want here. We just want a floor full of Legos so we can build whatever we want. Now, of course, I talk about this like it will solve world hunger. There are things that this does really well, and there are things that it has more trouble with, right? Because of course it's based on assumptions, and we can't unpack all of the things here. But let's just mention a couple of those. With regard to the variables that we have placed in our model, we can have variables that are, if we think about nominal ordinal interval ratio kinds of things, we can have variables that are these nice continuous variables of different scales. We can have variables that are, for example, binary or ordered categories. I will say we can handle it very easily. It just means that there's some more estimation machinery that needs to happen. And if you think about, if you have ever been exposed, for example, to regression, which we hope you have, then you might know that, yeah, it's okay to have a predictor that's binary. I can have a yes-no kind of predictor, first language, second language as a predictor. I can have something like that. When it's an outcome variable, though, then you might have realized that, oh, regression doesn't handle binary outcomes very well. But then there's something called, which you might have been exposed to, called logistic regression, which is an extension of regression to try to accommodate that as part of what's called a generalized linear model. So these kinds of overlays exist in structural equation modeling as well. What's a little bit trickier, not insurmountable, but very atypical, is when you have variables that just had a purely nominal. So if I had a variable where each person designated one of four first languages, like, oh, what do I do with that? This a 1 is not less than a 2, is not less than a 3, is not less than a 4. Then there are other types of models that handle truly nominal variables, or some of you might know that you could try to dummy code those and tease it out in some way, but it's a bit clumsy, quite honestly. So we're going to assume that the variables we have are fairly continuous, or if they are binary, then we can handle those too. With regard to the paths that we have in our model, the nice thing about the paths that we have in our model is that they are the connections that correspond to our theory. And something I said previously is that the paths that you see correspond to your beliefs about what might be influencing what, and the paths that you don't see mean that it means you were brave enough to say there's no reason that there would be that relation there. And so anytime you don't have a connection in your model, it's kind of like pat yourself on the back. You've stuck your neck out there and said, I am willing to say that this system is simpler than having all things connected to each other. that means that your model is a little bit more parsimonious with each such restriction that you impose on a model. And when you start imposing such, and I don't ever want to tell somebody to start taking out paths or restricting them that they don't, if they didn't believe that that was a reasonable theory. But the person who just says everything's connected to everything else isn't really doing a whole lot of theory testing, because a model like that has a habit of fitting no matter what data you throw at it. So models start to become testable when there are restrictions, when you stick your neck out there and say, I don't think there's any reason for that to be related. I don't think there's any reason for that to be related, and so forth. You create something where we start to be able to assess whether your more parsimonious representation actually has good fit to the data or not, because you're creating opportunities for it not to fit, which I love. All right, so we're going to dig into this a little bit more in the bottom part here, where we will talk ever so briefly about model fit. It is a massive area with a lot, I mean, still, structural equation modeling was born in like 1972, plus or minus. There's a little confidence interval around its birth year. But the idea of fit is really still evolving. People are challenging our notions about how do we assess the fit of some entire giant system. So I'll say just a tiny bit about that we could spend literally hours talking about. And then some other ideas, variance and covariance, model fit indices, and modification indices. So let's pop into here the notion of model fit. So we have a model, and that model is represented by a picture, right? When you're sitting at the pub and your friend says, "What are you working on?" You grab the little bar napkin and you write your model on it and you slide it over and you go, "That's what I'm working on," right? And in that particular picture, what you are hoping is that the connections among those variables can ultimately have numbers attached to them in a way that that corresponds to how you actually observe the variables in real life, varying and co-varying. And if you do a good job, yay, then you have reproduced the variances and covariances that data actually have. And if your model just can't do it, if we can't find numbers to go on those different paths that would yield something that's consistent with your data, we would want to know that too. But it would make you sad, because you'd say, "Oh, I guess my model is not doing such a great job." So we are looking for parameters. We're looking for parameters, just numerical descriptions in the population that correspond mostly to the arrows that we have in our model, in a way that is consistent with the variances of the variables that we actually observe in data and the covariances between variables that we observe in data. Or if you just like to think in standardized mode, you would say the correlations between variables. And each time we have been bold enough to impose a restriction to say, nope, I don't need a path there. Nope, I don't need a path there. Every time you impose a restriction, then the question is whether or not the model still stands up, because you are giving it less flexibility when you have fewer connections. And does it still explain the system that's going on? That will allow us to assess the data model fit. And one way to maybe visualize this, I don't know if it's helpful for you, but imagine that you have some theory. And this theory says that I have 3 variables over on the left, all of which are hypothesized to correlate with each other. They're all, who says? Well, theory says. That's why we put 2-headed arrows among them. Okay, that's cool. And 2 variables here, which are hypothesized to be influenced by some of those independent variables, 1, 2, and 3, not all of them, right? Variable 5, apparently someone was bold enough to say, nope, there is no reason variable 1 should have an influence on that. And that's why there wasn't a path there. Ooh, bold. And then we get to variables 6, 7, and 8. Those are hypothesized to be influenced by 4 and 5 directly, but you'll notice variables 1, 2, and 3, there are no direct paths from 1, 2, and 3 to 6, 7, and 8. Why? Because the researcher thought that variables 4 and 5 mediated the entire relation between 1, 2, and 3, and 6, 7, and 8. All right, well, so we go out and we gather some data, and we'll just imagine them in the form of a correlation matrix. The question is, are there numerical values that can be attached to these connectors that would be consistent with the pattern of relations that we have in our data? For example, we have a block here of correlations, and don't fuss with the actual numerical values there. They're just kind of placeholders. But that's a block of relations between 1, 2, 3, 4, and 5. So are there numerical values that we can assign to these things that would be consistent with those observed correlations? And with those correlations, and with the correlations of 1, 2, and 3 with 6, 7, and 8. So the idea again is picking numerical values, if at all possible, that are consistent with the data that we have observed. And in the end, have we done it? I don't know. There are a whole bunch of different fit indices that try to capture the extent to which the variances and covariances or correlations that you observe in the data are consistent with what your model says you should observe. That's what we're trying to assess the fit of. And sometimes your model has good fit, and that's what you hope for, right? You feel like your whole career hinges on, oh, I got to get good fit. If you don't get acceptable fit, then it means there's some aspect of your model that is notably wrong. And as a scientist, you should say, that's very good information for me to have, right? As someone who's heavily invested in your theory, you're like, oh, right? So you're not so happy, and you need to talk to somebody about that. But in the end, you get some assessment about whether or not your model has reasonable fit to your data. And there are many fit indices that we get out. What that means is a lot of people, alive and dead, have proposed ways to characterize whether a model is doing a good job or a model is doing a bad job. We're going to see these acronyms played out a little bit in some software in a bit. I'll say the words associated with them right now: comparative fit index, root mean square error of approximation, standardized root mean square residual, blah, blah, blah. But there's a whole literature out there that talks about, when is an index telling you your model's doing a pretty good job? When is an index telling you your model's not doing such a good job? And the real interesting part is that we have multiple such indices, and they don't always agree. You know, whereas previously, like Tove said, sort of p-value did all the thinking for you. Here we gather evidence about in what ways might our model be successful, in what ways might it be lacking, and that is really diagnostic information. All right. It is also the case that when your model doesn't fit particularly well, that software will often say, hey, come here, let me show you something. And it will pull you off to the side and say, I've got some ways you could change your model here. It might or might not have anything to do with your theory, but it will sure make your model fit better. And so software, whether it's Lavon or M+ or other software packages, will have what are called modification indices. And again, the program has no idea what makes any theoretical sense, but they are ways that you can improve the fit of your model. The challenge is it might make no sense whatsoever. And structural equation modeling is intended to be a fairly confirmatory framework, that you come to the table with the theory. And so modification indices in many respects are when you've said, yeah, that didn't work out so well. What do you got for me? And then maybe you treat this as something that is informative for the next stage of your research, learning from what you've done. So modification indices, are we allowed to use them? Yes, you know, as long as you have a very good theoretical filter operating, and we'll take a look at those. How do we use them? Well, we'll see that in the context of an example coming up. Here is some output from Lavon, which if you are smart and look at stuff with Tove when some of the rest of us go off and play in our room, here are modification indices. Now, there's a lot of information associated with this. Probably the most important numbers for our purposes will be like in the MI column. MI stands for modification index. And the bigger the number, it's in chi-square units if you care, the bigger the number, the greater the impact is expected associated with you making a modification that is listed here. So for example, I have this particular model here. Okay, that starts to make some of the words and labels make a bit more sense. What this particular model, being fit to the data, is telling us through modification indices, it says, you know, this relation right here, and you would have to speak a little bit of Lavon, that if you had adjectival modification have a direct path from prepositional modification it would improve the fit of your model by 16 chi-square units. And my the chi-square part of my brain goes, ooh, might not make any sense, but that part of the brain doesn't know that. It also says, and you could put a path to prepositional modification from adjectival modification, which is different directionally for sure. And it would be estimated that your chi-square would improve by about 12 units. And that chi-square part of my brain doesn't quite light up as much as it did at the first one. Again, might or might not make any sense. Modification indices also say, and this is something, again, if you start to get familiar with Lavon, a little two tildes, two squigglies, means that if the residuals, the errors between those two things covary, in other words, if there were common external forces that were influencing both adjectival modification and prepositional modification, then we would say, oh, yeah, well, that would improve the model by about 16 chi-square units. And we put a green box around that because you might actually have a theoretical rationale for what those external forces are, those common external forces that would lead them to covary, but the other two things might not make any sense to you, that adjectival modification causes prepositional modification or vice versa. So you see this information and it kind of makes you light up a little bit, but this is all after the fact. So this is when you're in salvage mode to some extent. Oops, I'm sorry. All right. So let's go ahead and, Tove, am I forgetting anything or are we doing okay?
I think we're doing okay. And maybe this is the time when we stop the recording too, before we move over to the hands-on exercises.
Okay.